Our next speaker is Jian Tang from Miller. Are you ready?
Yes.
Great.
Okay. So first, thanks, Regina, very much for the invitation. It's a great honor to be here. So I'm actually not a biological person. I'm pretty much like a classical machine learning person. But recently, I'm very fascinated by the biological world, and also see big opportunities in applying or in developing like deep learning methods for very challenging problems in biology. So today I'm going to talk about our recent progress in molecule modeling, specifically how can we develop deep learning models for molecule conformation generation. So, like molecule modeling is a very fundamental problem in many applications, like in drug discovery and material discovery, right? For example, we want to predict the properties of the molecules. So traditionally, the molecule are usually represented with a 1D smile string. And then recently, we see huge progress in representing molecules as two-dimensional molecular graphs. So specifically, we can use graph neural networks to learn the reputations of the molecules. However, for molecules, more natural and also intrinsic reputations are their 3D conformations, right? So each atom is represented by their 3D coordinates. Because actually the 3D conformations actually determines the biologic and the physical activities of the molecules. For example, how do they interact with other molecules? However, in practice, for most of the molecules, their 3D structure are not available, right? So therefore, a very fundamental problem here is how can we predict and also predict the valid and also stable conformations? For example, given a molecular graph, can we predict their 3D conformations? So this is a fundamental problem we're trying to solve here. For such a problem, traditionally, this is usually done by experiments. For example, we can use methods like crystallography and then try to figure out the conformations of the molecules. However, for the experimental methods, they are very expensive and also very time-consuming. And in recent years, we see huge interest in computation methods. For example, methods based on traditional molecular dynamics and also Markov chain Monte Carlo methods. Okay, so for the computation method, they are definitely more efficient than the experimental methods. However, they are still very computationally expensive, especially for very large molecules. And very recently, we actually see a huge progress and also interest in developing data-driven methods, or more specifically, machine learning approaches for molecule generation. Okay, so here basically we are given a large set of like training data. So we have a set of molecules, and for each molecule, we are also able to obtain a set of like conformations. Okay, and based on this training data, we want to model the distribution of the conformation R given the molecular graph. Okay, so this is the fundamental machine learning problem we're trying to solve here. Basically, trying to model the conditional distribution of the conformation R condition on the molecule graph G. Okay, so for such a problem, even from the point of view of machine learning, it's actually very challenging for two reasons. The first reason is that the conformations are actually rotation and also translation equivalent. Suppose you rotate and translate the conformation, they're the same, right? But the coordinates of the atoms will be changed. Okay, so this is the first challenge. The second challenge is that because each molecule can have like multiple different stable conformations, that means this conditional distribution of the conformation condition on the molecular graph is actually multimodal. So it's very complex distribution. So we must develop very flexible and also general models to model such kinds of like distribution. So in this project, inspired by the recent progress of deep learning models in machine learning literature, we developed a very flexible general model to model the distribution of the conformation R condition on the molecular graph based on normalizing flows. So normalizing flows are some very latest techniques in deep learning model in machine learning literature. So I will give a very brief introduction later. So in order to model this distribution, actually our process of the conformation generation can be divided into two stages. So first, given the molecule graph, we first generate the pairwise distance between the atoms, which is called like D. So the good thing, so these are the first step. And once we generate the distance between the atoms, and then we further generate the conformation R based on the distance and also the molecular graph G. Okay. So the good thing of first generating the pairwise distance between the atoms D is that so the pairwise distance among the atoms are actually translation and also rotation invariant. So that's why we treat the pairwise distance D as the intermediate variables. Okay. So in other words, we can divide this distribution into the product of two distributions. First generate the distance D and then generate the conformation. So this is the first part of our model. And in the second part of the model, we because sometimes for this model, for this flow-based model, it's not perfect. And then we further trying to modify this distribution with an energy-based tilted return E phi Rg. So this E phi actually estimate the energy of the conformation based on neural network. Okay, and then the final distribution of the conformation condition on the molecule graph will be multiplied by the flow-based model and also correct by the energy-based model. So I will give more details later. Okay. So let's have a quick look. What is normalizing flow? Why is it so powerful? So basically, normalizing flow defines an invertible mapping from a base distribution to a complex distribution. So usually the base distribution could be as simply as like a Gaussian distribution. And then the complex distribution usually are the distribution of the real observation data, like images, or in this case could be the distance between the atoms or the molecule. And then we define an invertible mapping between the base distribution to the complex distribution with multiple like transformation functions f, right? So each transformation function f theta can be implemented with a neural network. Okay, and in practice, we can estimate all the models with maximum likelihood estimation. And then in order to calculate the likelihood of the observation data, we can use the change of like variable theorem. So you can see this probability can be evaluated in this way. So the good thing about the normalizing flow, you can see that we can calculate the exact likelihood, and also the model can be flexible to model very complicated distribution. Okay, so next, and then we use the normalizing flows to model the distribution of the pairwise distance between the atoms and condition on the molecular graph G. We propose a model called a conditional graph continuous flow. Okay, so the essential idea of this model is basically we define an invertible mapping between the base distribution and also the pairwise distance between the atoms. So here is the vector of the pairwise distance among atoms on the molecular graph. So each element is a distance. Okay, and then here is a base distribution. So each element is actually sampled from a base Gaussian distribution. And then what we're trying to do here is we're trying to define an invertible mapping from the base distribution to the distance of the among the atoms on the graph. So in practice, one thing we can do is we can apply multiple discrete layers of neural network to define the transformation. So here, so instead of like using define the discrete dynamics of the distance, so we actually define the continuous dynamics of the distance with some latest progress in deep learning, which is called like neural ODE mechanism. So basically, for the neural ODE mechanism, we define so here we define the derivative of the distance over the time using a neural network, so which is the f theta here. So specifically, we use graph neural network because this is actually conditioned on the molecular graph. Okay. And once we generate the pairwise distance among the atoms, we further generate the conformation R based on the distance and also the molecular graph G. So we specify this distribution using an energy-based model. So the essential idea of this distribution is that we try to find the conformation R which are able to, you can see this is a conformation we're trying to find. So we try to find the conformation which is able to satisfy the given distance. So this is the essential idea. So this is the first part, which is based on the flow-based model. Okay, and then the second part, as we just mentioned, so we further try to modify this distribution with the energy-based tilting turn E phi R zeta. So remember, this E phi R zeta RRG is basically estimate the conformation of the current conformation, estimate the energy of the current conformation. So this energy is actually estimated by a neural network. So here basically given the molecular graph G and also the current conformation, we use a neural network to estimate the energy. So specifically we use SCHNet. So SCHNet is basically sort of like a neural massive passing function on the 3D dimension space. So basically, given the 3D conformations of the molecules, we can do massive passings among the atoms, and then eventually we can pull all the information from all the nodes to get a scalar value, so which correspond to the energy of the conformation. Okay, so you can see the final distribution of the conformation R is composed with two terms. The first term is the flow-based model, and the second term is energy-based model. Okay. So in practice, it's actually very difficult to train energy-based models because we have some normalization terms, right? And then so we can use some maximum likelihood method to train energy-based models. But in order to train energy-based model with maximum likelihood, so this usually involves a sampling process from the model, so which involves like MC or large event dynamics. So this is very slow, right? So here, instead of using the large event dynamics or MC for training the energy-based models, we actually train the energy-based models with negative sampling. Okay, so essentially, the essential idea here is we try to train a discriminator to distinguish between the positive conformations, which are the conformations we observe in our training data, and also trying to distinguish those true conformations from the negative conformations. So the negative conformations are actually generated from the flow-based model we defined in the first part. So that's how we are able to estimate the energy function. So basically, we want to find the energy function which are able to distinguish the positive conformation and also the negative conformation. So this is the high-level idea. And the final sampling process of or the process of generating a conformation looks like this. So we will sample a random variable from a base distribution, and then after some continuous like flow dynamics, so we are able to calculate, we are able to generate the distance. So we are able to generate distance between the atoms on the molecular graph, and then based on this distance and also the molecular graph, so we will find a conformation which is able to satisfy the distance constraint using gradient descent method. So this part is also very efficient. And then so by far then until this step, so we are able to obtain initial conformation. And then we further trying to refine this initial conformation using the energy function. So here the energy so this energy function is learned by through the negative sampling technique, and then basically we can do MC sampling. So we're trying to modify the conformation in the way that we are able to further reduce the energy. So eventually, and then we are able to obtain a stable conformation of the molecule. Okay, and then let's look at some results. So we actually use two data sets. So one data set is called like a Jian. So this is actually the data set developed by Rafa's group. I believe like in the next talk, Rafa is going to give more details on this data set. Okay, so this data set contains like more than 30 million molecule conformations, including both small molecules in the QM9 data set and also medium-sized drug-like molecules. So another data set is also built on QM9, so which contains around like 200 molecules. Each molecule has around like 5,000 conformations. And then we compare a bunch of different baselines. The first method is actually a very simple approach. So basically they use graph neural network to learn the atom reputations. And then based on the atom reputations, they directly predict the coordinates of the atoms. The second one is still we tried using graph neural network, but instead of like trying to learn the feature reputations for each atom, we try to predict, we try to learn a feature repetition for each edge. And based on the edge repetition, we first predict the distance among the atoms. And once we have the distance, we further generate the conformations. The third baseline is RD kit, which is basically a very classical force field in traditional molecular dynamics. So here are some examples of the conformations we generated by our algorithm. So here is a given molecule graph, and here is a set of like conformations sampled from our algorithm. So you can see our algorithm basically can identify, can sample very diverse conformations of the molecular graph. So here shows a visualization on how the conformations are generated by our algorithm. So you can see that our algorithm are able to transform from the very base noise distributions to the stable conformations. So here shows two examples. Okay. So this process is basically modeled by the flow-based dynamic model. So we can also look at some quantitative results. We evaluate the quality of the conformations using, we evaluate the quality of the conformations based on two metrics. One is the quality, another one is diversity. So for diversity, we basically evaluate the coverage of the conformations we generated. So we measure how much, what would be the percentage of the conformations in the reference set that can be identified by the generated conformations. So basically, for each conformation in the reference set, we compare it with the nearest conformation in the generated set. If the distance is more than the threshold, we think this conformation is already identified by the current samples. So this coverage. So another one is called like a matching. So basically, for each conformation in the reference set, we compare this conformation with the nearest conformation in the generated conformations. We use the distance as the distance between the two conformations to measure how well this conformation is covered by the current set. Okay. So here are some results. So here are the two baseline algorithms. So you can see our model is able to significantly outperform the two previous algorithms for molecular conformation generation. And then after further adding the energy-based Tang, we are able to further improve the performance. Okay, and then we also so these methods are totally like data-driven methods or machine learning approaches. And then we also combine these methods with some like traditional molecular dynamic based methods. So once the molecule is generated by the machine learning algorithms, we further refine the conformations using the classical force field methods. So we can see that the performance can be further improved if we further refine the conformations based on the traditional molecular force field methods. And then we also evaluate another way to evaluate the quality of the conformation is to evaluate the distribution of the distance among the atoms generated by the algorithm. So we evaluate the marginal distributions of the distance between the atoms, and also the pairwise distribution between two edges, and also the joint distribution of all the atoms in the molecular graph. And then we compare the distribution, evaluate on the reference set, and also the conformations generated by our algorithm. And for the two distribution, we use maximum mean discrepancy to measure the distance between the two distributions. So here are some results. You can see that our algorithm is able to outperform all the previous algorithms. And then a little bit surprising thing here is once we add the energy-based model, actually the performance decreased. But this is actually not surprising because the energy-based model actually will sharpen the distribution, which is actually not ideal for measuring the distance between two distributions. So to summarize, so in this presentation, so basically I talk about how can we use like a machine learning methods, in particular deep general models for molecule conformation generation. And then I think so I want to briefly mention the future work. I think in the future it's actually this is a very exciting direction. And right now, we basically only use machine learning-based methods or data-driven methods. But for molecule modeling, actually, there are some underlying physics model. For example, those physics model used in traditional molecule dynamics. So we are interested in how can we combine in the physics model and also deep learning method for molecule modeling. Okay. And the second point is that the method we develop here, the deep learning model we develop here, is actually very general, could be applied to model other structured data as well. For example, in the future, we will be very interested in developing deep learning models for protein structure prediction. So with that, I will stop here and take some questions. Thanks very much.
Thank you. Thank you very much. And it's very nice to see this new thread of really connecting, deep learning, molecules, and the underlying physics. This is really an underexplored area. And I think all the people who work on method, this is a great direction to move. Thank you for excellent talk. So let's see if we have some questions. Let me see. So we have one question. Have you considered applying this model to find conformations? Okay, it jumped again. So where did it go? Can you help me out here? Where was this question? Could you disappeared?
So I could briefly answer as also. I think I get the rough idea. So we haven't yet, but that's why I think in the future work I mentioned that we'll be very interested in collaborating with people in biology to solve many problems related to protein structure prediction or even docking problems. So I see there's huge potential in applying these techniques to those problems. We haven't yet, but I'm very happy to have the conversation or collaborate.
Jian, do you want to look briefly at the Jeff Blaney's question?
Okay. So internal distance are invariant to translation and rotation, yes. So that's why we first generate the distance before generating the conformation. Following on Padwa's question, how does this compare to energy embedding approach, which use distance geometry in a high dimension space to simultaneously optimize the pairwise energy function? Okay. I haven't looked at this paper. I'll be happy to take a look at this paper. But thanks for the reference.
Great. So, Jian, there are a few questions, if you will be so kind to answer them afterwards. And thank you very, very much.